Here's a brain twister. Ever look at a function and wonder, what if we can take this function and find its derivative, and then end up with another function, and then find its derivative, and then find another function, and then find its own derivative, and then again, and again, and again. Luckily, calculus allows for this, and I don't see why not. All under the topic of higher derivatives, where you can derive until there is nothing left at all. And here you can find the form d to the n times y over d to the x, or f to the n to the x. So finding a higher derivative is relatively simple. You just have to derive, which I'm sure we're all great at now. Here we get our first derivative. Then you derive again for a second derivative, and then you derive again for a third, for a fourth, for a fifth, until we get nothing. There's nothing left at all, it's zero. So let's say you have been approached by a strange man. He hands you a function and tells you to find the second derivative of the function, or else you'll die. Luckily for you, you're a calculus wizard. However, luckily for you, slipping on your whimsical math hat, you realize instantly that you, just like all other derivatives, just have to derive and then derive once more to get your second derivative. So here you start with your original function, and then you want to derive once to find a function, and then you end up with another function which you can derive once again to find the second derivative of the function. So what you want to use is just use your quotient rule, and just to find the first derivative of f of x, and you'll just use the quotient rule and just use 4x squared plus 4x plus 4. That's what you end up with, over x squared plus 1 squared. And then all you have to do is do it again. Really. It's really quite simple. So after a bunch of tedious work, you end up with the second derivative of f of x being 8x cubed minus 12x squared minus 24x plus 4 all over x squared plus 1 cubed. But why do you need to know this? Why is it essential? I mean, really, just looking at it, you just derive twice. But here, just to show a really good example of why it's pretty much want to learn this, we're just going to use the example of a accelerating car to find its acceleration. So here we have a graph that you've plotted based on the position of the car. We took a GPS and we've looked at how fast at the position every t seconds, and we found that it looks like x squared plus 5x plus 5. Now if you take the rate of change of the position, you get v of x, the velocity, which is just going to be the derivative of x squared plus 5x plus 5. And that we can see that once we plot that, we get 2x plus 5. And that will be the rate of change of velocity. Now the rate of change in velocity is going to be equal to a, or the acceleration. And that's just going to be a simple line, with y equal to 2 in this case. And that will be our acceleration. But scientists use this to find different things and approximate what we need to do to find correlations and to approximate further, well, actually extrapolate. Anyways, it's pretty neat.